Hi, and welcome to MSc. In this video, we're going to be looking at VSEPR theory, specifically the scenario where we have two electron domains around the central atom. So in the scenario where there's two electron domains around the central atom, there's really only one case to consider, and that's the case where both of these electron domains are bonding domains. As a reminder, as I talked about in a previous video, a bonding domain can be a single bond, a double bond, or a triple bond, whereas lone pairs are not in bonds, so they're a non-bonding domain. The reason we have only one case to consider is because if we only had one bonding domain, it would just be two atoms bonded together, and that's always going to be linear and isn't really of a ton of interest as far as VSEPR is concerned at this level. In this scenario, we still do have a linear molecule. The central atom and the two atoms on either side will arrange themselves in a straight line as the two bonding domains try to get as much space between them as possible. This also means that the molecular geometry will also be linear. So not only is the arrangement of the electron domains a straight line, but the actual molecules also line up in that way as well. The electron domain geometry and the molecular geometry will always be the same when all of the electron domains are bonding domains. And you'll see that in other examples throughout other videos where I talk about 3, 4, and 5, and 6 electron domains. Also, if your curriculum also includes hybridization, it might be of interest or important to note that this scenario will always result in what's called sp hybridization of that central atom. This purpose of this video is not to talk in great detail about hybridization, but more to make you aware that there is a link between the electron domain geometry and the hybridization. So let's look at an example here to start. I'll try to do 3 of them quickly through this video. And the first one is probably the most common example you'll see on two electron domains, and that's carbon dioxide. And the first step is to draw the Lewis formula or Lewis structure. So we have to do this by counting the number of valence electrons available to us and then drawing them out appropriately. So you might already know what this looks like, but carbon is going to allow us to have 4 valence electrons, and there's 2 oxygens, and each of those have 6 valence electrons. So this allows us to have 16 valence electrons in total to draw out in our picture. So in this, we can see that carbon's going to be in the center with oxygens on either side, like so. And then you can start to figure out how to place. Each of these bonds here that we've drawn already represents 2 electrons each, so I'm down to 12 electrons remaining. You can see if I tried to obey the octet rule and did something like this, where all of those are lone pairs, this has a couple of lone pairs, and this has a couple of 3 lone pairs. I have too many electrons drawn in this scenario. This is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So that's way too many. So what we can start to do here is, at this point, we can then say, okay, well, what if I didn't have a lone pair here, and what if I got rid of a lone pair there? And instead, I had a bond there. Well, you can count them and you'll still see that you're not quite right. Even though this has the octet rule, this does, and this does, then you can try that same type of method again and get rid of one of the lone pairs and get rid of that lone pair and draw the double bond. And this obeys the octet rule and adds to 16, 2, 4, 6, 8, 10, 12, 14, 16. Now typically this will be redrawn with these lone pairs kind of spaced out a little bit better in 3 dimensions, or I guess on the page in 2 dimensions, and you'll see it more commonly with them angled like that. So this does have a linear structure, and it is a 180-degree bond angle. And so that's important to know that this linear geometry will result in the 180 degrees. And this one is pretty consistently going to be 180 because it doesn't matter if this is single or double bonds, they're going to get as far away as possible, and that's 180 degrees. So even if you have a single and a double, they'll still be 180 degrees. We don't get distortions from the linear, as you might see distortions from later examples in future videos. We can also see this if we take a look at using a PhET simulation. And so here's a simulation that's open for us looking at molecules through the simulator PhET, which is from the University of Colorado, which is a great tool if you haven't checked it out. You can toggle between real and models, and we can see this is CO2. I can choose from a wide variety. I can show bond angles if I want and see that it's 180 degrees. I can click on this too and rotate it around and see that in fact it is quite linear and it shows the double bond quite well. If I want to, I could also click the molecular geometry and electron geometry and see that in fact it is linear, as you can visually tell. So that's carbon dioxide. Let's roll through a couple more. Here we have BeCl2, and you might say, wait a second, is this an ionic compound? In fact, the electronegativity here is 1.6, so it is polar covalent in this bonding scenario. So you can try drawing this one out, counting the number of valence electrons like we did in the last example. I'll go a little quicker through this one. And we see that we have the chlorine with the 2 beryllium valence electrons, making those bonds. And then you can either use lines as I did for the lone pairs, or you can use X's or dots to show the electrons around the chlorine, whichever one you find most efficient. Again, I find the dashes are the fastest. I just know that sometimes with chlorine, the dash makes it look a little bizarre. Right? These have the octet rule, and you'll notice that the beryllium in this case is actually forming an incomplete octet, which is an interesting scenario, and you'll see incomplete octets and you'll also see expanded octets as we go through the different VSEPR scenarios. This, just like the other, has a linear geometry. It has a molecular geometry that's linear, which means that's its physical shape, and again its hybridization is sp. So this means that the angle that this forms here is 180 degrees, just like the CO2. One final example here, C2H2, or ethine. And if we draw this one out, which you maybe have drawn before, maybe you're familiar with the organics, maybe not, but it looks like this. We often draw it as a linear molecule, and in fact it is. We talk about central atom, but the central atom doesn't always mean the center of the molecule necessarily. We can focus VSEPR in and focus on just like one of the 2 carbons. Turns out that they're both identical in terms of their bonding structure here. But if we look at this one, we see a triple bond and a double bond. That's 2 electron domains, right? Just like all the others have had 2 electron domains around what we've been calling the central atom. This is also going to lead to a 180 degrees. And we can apply that same to the other one too, and we can also see that it's also going to have 180 degrees because it has those 2 electron domains around it. Right? Just like this had 2 electron domains around the beryllium, and carbon had 2 electron domains around itself. Right? Again, an electron domain can be a lone pair, it can be a bonding pair, or it can be double or triple bonds, so we call them bonding domains. So this has 2, it's going to be linear. This has 2, we know that it'll be linear. And lastly, we know that these bonds will be linear, so the whole molecule will be linear. And we also know that the hybridization on the carbon is sp hybridization, which will generate that linear structure. I hope this quick run through of using VSEPR for 2 electron domain scenarios to predict the electron geometry and the molecular geometry has been helpful. If it has, please like the video and subscribe to the station. And as always, thank you very much for listening and watching.